Okay, guys. Good morning, and get started. At the end of class, I'll pass back the polarimetry lab to Thursday's group. At the end of class. Okay, test on Monday. Last questions for test on Monday. Alkene chemistry, alkyne chemistry, and stereochemistry. No spectroscopy. This is the only test I give in Organic 1 or 2 with no spectroscopy. Test 3 will have mass spec. Mass spectroscopy or mass spectrometry. Today we'll begin resonance, which is test 3, but we've seen resonance in each test before. We saw resonance with acid-base chemistry, and we also saw a little resonance with detautomerization. Okay? Resonance. No matter what textbook you're using, it's going to have a chapter on resonance. Most books cover resonance like in chapter 1 or 2. I think it's too early to really dive into resonance. I think you need to become more familiar with Lewis structures and just dealing with organic molecules, orbitals, etc. Anytime a lone pair is next to a p orbital is going to want to be in a p orbital, yay? Well, that's really resonance. Most books don't tell you that until chapter 20, but I tell you that at the beginning because that's the core of lone pair conjugation. Other books actually lie to you about that in chapters 1 and 2. I'll never lie to you. Intro to resonance, also known as delocalized bonding or pi bonding, because we're dealing with pi electrons. Okay? We can first look at the idea of neutral conjugated alkenes. Dienes, and dienes is the handout I sent you by email. Please have that printed for next Wednesday. Dienes are compounds that contain two enes, two alkenes. This is a diene. Okay, simple as that. What if they contain three alkenes? Triene, very good. You have a bit of price. Okay. Both of these are dienes. The difference is this one's conjugated, this one's not. What does conjugated mean? First off, which one's more stable? Well, heat of hydrogenation is given. Which one's more stable? This one, because when you hydrogenate it, it gives off less heat because it contains less to begin with. Okay? Why is a conjugated diene less stable? Okay, important. Because it's conjugated. Well, what does that mean? Let's look at that. If you look at the p orbitals here, this is a p orbital, p orbital. One electron overlap of the two p orbitals makes the pi bond that we see there. Same thing over here. P orbital, one electron in each. Overlap makes the pi bond we see there. But look at here. These two p orbitals in the middle, number 2 and 3, are next to each other also. Are you telling me that they don't have any overlap? Well, actually they do. There's p orbital overlap between the two middle carbons. Now look over here. Pi bond. Pi bond. But look at here. Are these two p orbitals overlapping any? No, they are not, because in between we do not have a p orbital. The carbon in between is sp3. It does not have a p orbital. So there's no overlap between the two p orbitals. This here is one continuous pi system. It's one pi system with 4 p orbitals. 4 p orbitals all overlapping. Like toy soldiers, these p orbitals are all lined up, and they're actually all interacting. Pi bonding. This is not. This is two separate pi systems. Two separate pi systems. They're not interacting with each other because of that sp3 carbon in between. Which scenario has more p orbital overlap? One on the left. And more p orbital overlap is like more bonding. And more bonding is a stability thing. That's why this compound is more stable. Conjugated dienes are more stable. Conjugated means the p orbitals are all overlapping. They're conjugated. The two alkenes are conjugated. That's kind of the terminology. Here, the two alkenes are not conjugated. They're not lined up and overlapping because of that sp3 carbon in between. What we have to get past is looking at this and saying, hey, pi bond, pi bond. There's actually pi bonding here, though, which we can't see from these kind of just simple Lewis structure. But these orbitals are also interacting. Okay, what about this? This is called accumulated diene. The carbon is double bonded on both sides. It's kind of odd, accumulated. But it's also not conjugated, okay? Because, first off, what's hybridization of the middle carbon? SP. Okay, it's SP. Pi bond, pi bond. Are these two pi bonds conjugated? They're actually not, because the center carbon, we draw one p orbital, and then come over here and draw the CH2, draw this p orbital, one electron make pi bond. Now there's another carbon over here, but before we draw the p orbital here, this carbon is sp, meaning it has two p orbitals. I drew one. How is the other p orbital oriented? Perpendicular. Perpendicular. It's coming out. Now it's hard to draw, but I'm going to draw it sort of like this. That was supposed to be coming out at you. Okay? Well, guess how this one is doing? This one's also perpendicular. And you have one electron, and that's overlapping. But this pi system is 90 degrees to that pi system. So if this pi system is like this pi system is like that. And that is somebody help me here. Stand up. Thanks. Hold two p orbitals straight up. Two toy soldiers straight up. One here. Okay, here's the center carbon. The other p orbital's like this. Two p orbitals orthogonal, perpendicular to each other. But guess what? The other one over here is like this. So that's what you have here. And you have pi system this way, one alkene, and then the other alkene. Very good. Okay? Now, here's the question. Are all four of these orbitals all lined up with each other? Or are three of them lined up with each other? No. You got two lined up, and you got two lined up. Because for p orbitals to be lined up, they have to be like that. That would be three lined up. That would be four lined up. And we would say four p orbitals are conjugated. But guess what? It's not, because these two are like this. You have two individual systems. And these two are not conjugated with those two. Thank you. That's what you have with the, that's called an allene. It's called accumulated. Not conjugated. Okay, benzene. Benzene, all 6 are conjugated. All 6 are straight out of the board. All 6 are lined up around in a circle. And it turns out when you have p orbitals conjugated in a ring, completely conjugated, that's a very good stabilizing effect. It's aromaticity. Aromatic. Benzene is aromatic. It's a fully conjugated cyclic system. Aromatic. 6 p orbitals conjugated. And we'll talk more about aromatics in organic too. Okay. Here you have 4 p orbitals conjugated, but it's not cyclic. And so it's not this magical aromatic. But this is still better than that. It turns out once you make it cyclic, it becomes better than non-cyclic conjugated. Okay. Conjugated dienes are more stable than non-conjugated dienes because the p orbital overlap is like bonding. It's extra orbital bonding. And more bonding is better. Okay, resonant structures, showing dipolar resonant structures. This is actually sort of tough to work with because there's no heteroatoms and there's no polarity. But it's the simplest. It's actually right here, yeah. Maybe let me say a little introductory here. Pi bonds are polarizable, okay? Because the pi electrons are not held that tightly. For example, look at this. Double bond to O versus, I don't want to put an H here. So if I put an H here, we'd have hydrogen bonding, and that would make this more polar. Let's make this methyl. But let's look right here. Which compound's more polar? Well, you would say they both have dipoles, right? And then you maybe have a tough time saying which one's more polar. Well, this guy's more polar. Why? Because what did I just say 20 seconds ago? Pi bonds are very polarizable because the electrons are not held tightly. That is, this oxygen can basically pull these electrons up, the pi electrons. And if you did, what would you get? Well, what does that arrow mean? It means the pi electrons are moved up to the oxygen as a third lone pair. That becomes plus, that's minus. And this is a resonant structure. What is a resonant structure? A resonant structure is nothing more than just an alternative flow structure where all you've done is move pi electrons. You don't move atoms, because if you start moving atoms, you're no longer doing resonance, you're showing a different compound. But these electrons can be just very more easily and fully pulled up there. This is a sigma bond. The oxygen cannot just, these are held tighter. The oxygen can't pull it as much. And also, if it did, and if it just ripped them away, what would you get? You get that plus that. I mean, you would just rip them apart. Well, this is not resonance because this is no longer the same compound. So you're not doing resonance here. So two things. Pi bonds are very polarizable, and thus you get more of this polarized resonance structure. And thus we say this compound is more polar because it exists more like this. This can't pull as much. Sigma bonds are not as polarized. And you don't break sigma bonds. Resonance is only pi bonds. Because if you dealt with sigma bonds, you'd start breaking the molecule in half. Okay, that's just a broad overview of some things that may or not be specifically spelled out. I think it's a good introduction. Let's look at this. Now, I drew this because we have the oxygen, and we could say, well, the oxygen is more electronegative, it'll move towards the oxygen. Like I said, where are these electrons going to move towards? You know, carbon versus carbon. There's no inherent dipole or difference in electronegativity. That doesn't mean we still can't do it. It's just not as intuitive. Pi bonds are polarizable. What if we take this pi bond and do this? That is, pi bond, and take one of the bonds, which is 2 electrons, and move them here. Now there's going to be 2 electrons sitting here. That's just like I did right here. 2 electrons move on to oxygen. And what if these 2 electrons move on to carbon? What would that give? We didn't do anything there. And we now have what here? A lone pair. That's actually a minus charge. What's here though? Positive charge. It's the same thing we did here. We generated a minus and a positive by polarizing the pi bond. We didn't move any atoms. How many H's on the end? 2. There's still just 2 there. That's why it's a negative charge. If there was a different number than 2, it would not be a negative charge. Okay, you got to know where your H's are. Well, guess what? That's just a resonant structure. Why? Because it's just an alternative Lewis structure where all we move is pi electrons. Okay, let's go back and sort of start afresh and let me say 2 things. When you're dealing with resonance, there's sort of 2 approaches. There's a very theoretical approach, understanding the p orbitals and the theory. But then there's also the, okay, let's do this on the board approach. How do you draw a resonance structure? In terms of theory, this is just like this, except it just doesn't have the nothing. It's a conjugated diene, right? That is, aren't all 4 of these p orbitals lined up? Right? On each atom. These 4 can all be straight up, but because there's no, not here, they're not lined up. It's not a continuous overlap. Okay? Here we have a continuous overlap, conjugated diene, 4 p orbitals. It's just like here, except for not the methyl. And 4 pi electrons. Four p orbitals and 4 pi electrons. Because each p orbital contains 1 electron. Okay? We did something like, we did this type of thing during test 1 though, didn't we? How many electrons in the pi system? Okay? Now, theoretically, you can do this. P orbital, p orbital, p orbital, p orbital. They're there. There's your 4 p orbitals. 4 pi electrons. Put them in the p orbitals any way you'd like. I could put 1 there, 1 there, 1 there, 1 there. And if I did, I could then say, well, 1 electron overlap, make pi bond. And pi bond here. And which structure does this look like of those 2? This one. But I could also put them in maybe, what if I put 2 here, none there, 1 there, 1 there? Now the pi system has 4 pi electrons. Well, what would that look like if we made that a pi bond, made that a lone pair, made that an empty orbital? What would that look like? Look like this one. These are just where the pi electrons are just sitting in different places. Whenever you have conjugated system, it becomes really like one system. Okay? This is like one system. And the electrons are really just spread out all in that system. And this becomes no longer an accurate depiction of the true molecule. This looks like there's 2 here, and there's none in between. It's actually not. And sometimes at this point can give sort of an analogy. What if I brought in a garden hose that was 4 feet long? There it's laying on the table, garden hose. And then what if I put water in it, filled it up, and capped the ends off, like the polarimetry tube? How would the water spread out in the garden hose? Would it be uniformly? Or would half the water be here and half the water be here? It'd be uniformly throughout it. That's actually what's going on here. And the structure we have drawn here doesn't accurately depict that. Now over here, well, we erased it. I'll go back to the analogy down the road a little bit. That's really what's going on. Drawing resonance structures, we can just move the electrons where the arrows, this gives this. From here, can we draw another resonance structure, something different than these two? What if I take these electrons and move them there? Is that going to be something new, or will it give like this? That arrow movement would give this back. So that's not going to lead us to a new. Over here, what if I take these and move them here? What would that give? Show what that gives on your paper. We didn't do anything here. It's still a minus. Actually, now, what do we now have between these two carbons? Pi bond. Okay? This is like a windshield wiper moving over here. Now what do we have on this carbon? It's missing a bond. It's actually now a positive charge. That arrow gives that resonance structure. The double-headed arrow here is a resonance arrow. That means we're showing a resonance structure. But this is just another way to show the structure. That's where we put 2 electrons here, 1 there, and none there. So there's 3 different resonance structures, and we can maybe draw even more resonance structures. But this becomes a question. Of the 3, which one do you like better? Which structure do you like best for this molecule?
One with no charges.
Yes, this is best. This is called the major resonance structure. Because there's no charges. And this one looks like the electrons are more equally distributed throughout, like would be in that garden hose. I mean, why would some of the water in the garden hose be more towards this left end? This looks like more of the electrons are towards the left end as opposed to the right end. Why would it do that? I mean, they're both carbons. Why would this carbon want more electron density than this one? It wouldn't. You have no reason to polarize it like this. So these are like, yeah, they're resonance structures, but they're not that good. I like this one best. Major resonance structure. This is something important, though. Every resonance structure has the same net charge. This is a neutral molecule. Well, it's still neutral because you got a plus and a minus. Net neutral. Net neutral. If all of a sudden your structure becomes like net minus, then something's wrong. Every resonance structure has the same net charge. And we've already said 2 or 3 golden rules. In the back of the handout, there's a list of these rules. probably number 1 or 2 says that every resonance structure has the same net charge.
So are there cases though when like you had a charge on, say, an oxygen or something, that would be the major resonance structure because you want to polarize something?
Yes, like the one I drew originally. It may not be major, but it would be more reasonable than here. Because ultimately, no charge is better, even if we have an oxygen. But more of these examples will come up as we go along. We're building, okay? As we do more examples, we build, you organize your thoughts. Question?
Yeah, since those two would be considered minor resonance structures,
Minor, yes.
are one of them more preferred than other?
I mean, from a physics standpoint, this is probably better because at least the charges are closer. There you have even more charge separation. But probably main thing is just say, hey, this was better. You're trying to say, hey, which three-legged horse is the fastest? I mean, they're both pretty darn slow. But they are resonance structures because all we did was move pi electrons. We actually had resonance structures on the board on day 1. Because we did a Lewis structure and we said, okay, we fill the valence of oxygen first. Okay, and then we would say, well, how do we get another bond here? What did we do? We took these electrons and moved them in. Made pi bond. Well, but right there is a resonance structure. Okay. I erased the structures, but you still got them there. We need to make a comment on resonance hybrids. Wish I hadn't erased them, but you got them. Look between carbons 2 and 3. What's the bond order between 2 and 3? Bond order is it single bond, double bond, triple bond, or is it bond and a half, or what? As drawn, what's the bonding between 2 and 3? You see a single bond. So if it's just purely a single bond, bond order would be 1. Is the bond order 1 or is it greater than 1? It's actually greater than 1 because there's actually some pi bonding in between. Bond order greater than 1. Look at the other resonance structures. What type of bonding did we have between 2 and 3 and the other resonance structures? What about the second resonance structure we drew? Was the bond order 1 or 2 between that one? Second resonance structure we drew. Well, not the first one we drew, the second structure. What's the bond order between carbons 2 and 3?
Second resonance structure, the second structure.
Second structure. I mean, they're all resonance structures, but we drew 2. The middle structure. Bond order was 1. What about the third structure? What's the bond order between carbons 2 and 3? 2. Look at that resonance structure. The bond order is 2. That resonance structure tells you that the bond order between 2 and 3 is more than just 1. We see that it has some bond order of 2. Now the true structure is a blend of all your resonance structures. If you blend all 3 of those, if you average all 3 of those on the paper, what's going to be the bond order between 2 and 3? Is it going to be exactly 1 or is it going to be more towards 2? Like 1 and a third. Yeah, it's going to be a little bit more than 1. The electrons are really spread out in between here also, and one way to draw that is like this. not good, but this would be a resonance hybrid. The hybrid is where you're going to have partial bonds. Partial bonds are hard to deal with. The partial bond is more of the true structure. This is a little bit cumbersome to do here. We'll do this again when we move down below. And I'll erase that. Let's do it down below. Okay, resonance is actually easier in some regards when you have a charge to deal with. And down below, let's look at resonance of cations. A little bit easier because when you have a charge, you can just kind of focus on it and begin with it. And it helps get you started in assessing what's going on. This is just a carbocation. But it's going to have conjugation. Okay? Theory and then practice. Let's do the practice first. Let me draw a resonance structure of this. Importantly, how do you stabilize a cation? Do you move electrons towards it, or do you want to move electrons away from it? You stabilize a positive by moving electrons towards it. We have these pi electrons over here. We can take these and move towards it. It's like a windshield wiper. Boom, pi bond over there now. What does this give? What does that arrow movement give? We now have pi bond over here, and now what do we need to show here?
Positive.
Positive, because that carbon has lost a bond. You've got to know where the H's are. How many H's on this N carbon? 2. How many on the other N carbon? 2. There's a resonance structure. And that's the only one you can draw. Unless you polarized this pi bond and created 3 total charges. But that would be like a 3-legged horse. Let's don't do that. So I'm not going to show a terrible resonance structure. Question?
But isn't that the same thing as this one just turned around?
Well, they are similar, but they're not the same thing. They are the same, but they're not. We'll talk more about that. It is something new, but it's got identical energy. That same energy. Because if you want to talk about major or minor, which one's major? Which one do you like better? They're equivalent. Okay? We call this equal contributors. There you go. Okay, here we can talk about hybrids and true structures, etc. a little bit better. Since these are equal contributors, and this is also reasonable. But first let's do theory. What's the hybridization of this carbon here? sp2 with a p orbital. It has a p orbital. Okay, how many electrons in the p orbital? It's empty. That's why it's a positive charge. Then over here we have one electron pi bond. Okay? How many p orbitals are conjugated here? 3. 3 p orbitals. How many pi electrons in the system? 1, 2. 2 pi electrons. It's missing an electron, that's why it's positive charge. Okay. There's your conjugated system. And there's 2 electrons spread out equally through here. Okay? These are actually two fake structures. Resonant structure. What does the hybrid look like? A hybrid is where you blend these two together and you say between the first and second carbon is single bond. Now we have double bond. What's the average of single and double?
1.5.
1.5. Over here, between 2 and 3, we have double and single. What's the average of double and single? 1.5. Charge. What's the average of positive and neutral? Partial positive. What's the average of neutral and positive? Partial positive. Okay? This is your resonance hybrid.
And that's actually what the true structure more accurately looks like, if we could actually see it.
That is, the electrons are not just sitting here and here and this empty. It's not just that. Because this is empty, some of this electron, like the water in the garden hose, some of it flows this way too. And what you have to get across is, once you have one pi system, the electrons are really spread out here freely. Okay? Does it make sense if you had a garden hose and the water came in here and just stayed over here? Or will it spread out equally in the garden hose? And they'll spread out equally. That's what's going on here. Once you have conjugation. And once it spreads out, it no longer looks like either of these. This is the true structure. If we could look at the electron density would be the same between each carbon. And we also go back to major versus minor. Are either one of these preferred? Or are they equally preferred? They're equal. So they're both contributing the same degree. You've got some positive here, but you also have some positive here. This is the true structure. The problem is, how do you work with a half a bond? It becomes very cumbersome. These are much easier to work with. We just have to realize that this is really the true structure. It's a hybrid. Okay? Look at here. How many can you draw resonant structures of this? You can actually draw more than one here. Draw at least one here. And also answer this. How many p orbitals in the system? How many pi electrons in the system? Okay, we have a cation. How do you stabilize a cation? Move electrons towards it or away? Towards it. Okay? Windshield wiper. This pi bond, you can draw that line or that line. Moves towards it. What do we get? What does that arrow movement give? Boom, we now have pi bond over here. We didn't do anything here or here. What do we show here? That carbon lost a bond.
Positive charge.
Positive charge. There's a resonance structure. It's an alternative Lewis structure where all we move is pi electrons. Can we do another resonance structure? We can keep going. These electrons can move up here. That is, boom. What does that give? Didn't do anything here. Now have pi bond here, there, and plus charge here. And we can actually keep going. These electrons could come over here. And we can get positive charge there. And then next, we can pull these down. If we pull this down, what would that give? It's kind of the same thing. The pi bonds would now be here, here, here. The charge is back on that carbon, but the pi bonds have been moved into green. So is that really a different resonance structure? It strictly is, because these here are resonance structures. Sometimes that would not be included here. To get to here, you can move these electrons, but you wouldn't move the charge. You can move these electrons by moving these here, moving these here, and moving these here. That would give you back this. I hesitate to show that because it's really a kind of a second point. Which structure do you like best? They all have charge. Any of these better than the others? Actually, this one's best because the benzene ring is maintained. These are all resonance structures. Here's an important concept. Let's compare that to that. To that original and this. Which cation is more stable? The one on the right or this one? This cation's way more stable. Why? Because the resonance has delocalized the charge. What's the true structure of this? Is this the true structure, or is it a hybrid that includes all of it? The true structure is, what do we have between here and here? Single bond? Double, 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 single? So what do we have actually between here? Is this really just a single, or is it more, some more double bond character? It's got some double bond character. And it's between. And actually, it's the same thing all the way around. Single bond here, single, single, double. Actually, if you look all around, it's like this all the way around. What about charge? Plus here, but it's neutral, 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 plus. What's the average of plus and neutral? Partial plus. What other atoms does the partial plus fall on? That one, and that one. The partial plus never falls on that carbon. Here's your hybrid. If you could look at the molecule and see the electron density, it's really spread over like that. If we had to say which one does it look more like, it looks more like this one because we said that's a major. Okay? But when you're drawing your hybrid, it's hard to say it looks more like that one unless you want to make this heavier, make that lighter. But usually when you draw your hybrid, it's just sort of showing a blend. But here's back to the main question. Which cation is more stable? One that's sitting right on one carbon? Would you rather have a positive charge on one carbon or spread over the whole molecule? Yes. The charge has been delocalized by resonance. And that's a very stabilizing effect. Resonance stabilization of the carbocation. Can you draw resonance here? You have one p orbital. Does that have a p orbital? No, it's sp3. Does that? No. We got one p orbital. It's one orbital. It's not conjugated with anything. It just can't do anything. There's no resonance. This is a great cation next to the benzene ring because of the resonance. It's called a benzylic. Cation. Very stable by resonance. Question?
Why is the left benzene molecule more, like why is that an energy product over the one on the bottom?
Over this one?
Yeah.
They're really the same. That's a different discussion. I almost wish I had drawn that one. But whenever we look at benzene, benzene has two resonance forms. These are actually just resonance structures. One thing that's important here is usually when I ask you to draw resonance structures, I'll say that involve delocalization of the charge. If I just drew this one, the charge has not been delocalized. It's still there. So you wouldn't want to show that one if I said draw resonance structures that involve delocalization of the charge. It doesn't involve delocalization of the charge. But those three do. This is what it really looks like. But guess what? If we tried to do react mechanisms with this, it'd be like, how do I deal with these partial bonds? That's why when we actually do chemistry, we'll work with these structures. But guess what? These are really fake. They're not the best representation of the true structure. This is the best representation. That water is spread out equally through here. Actually, there's a little bit more water here. Like we said, this is kind of preferred to be in here. Okay, we didn't make as much progress as we should have today. I gave a good amount of theory background. Please do this. Resonance structures, please draw them. We'll have heteroatoms here. You got pi bonds, but you also have lone pairs. Lone pairs can be used in resonance. Okay? Please have a lot of this done for Wednesday. I'll move through it quickly on Wednesday. We also have examples of how resonance can affect reaction outcomes. Please attempt this. Realizing that if you have a carbocation intermediate, a resonance stabilized cation is going to be better than a non-resonance stabilized cation. Resonance is very powerful in stabilizing carbocations. For Thursday's lab, you can pick it up on the way out, polarimetry. Did y'all cover sig figs and Gen Chem? I'm not sure if you really learned how to do it or if you just did it to pass a test. Because some of you seem like you don't know how to do sig figs. If it wasn't covered in Gen Chem, let me know. Have a good day, guys. This is Thursday lab only. The other lab will be this afternoon. Downstairs. Lauren Ingalls, staff. Here. Emily, Elizabeth,